Hi, in this video I will do a short review on applications of differentiation, and then I'll show you how to solve some basic problems in this chapter. Okay, so basically in this chapter we work with the first and the second derivatives. Let's do a short review on the first one and on the second derivative, right? Um, the first derivative have us to find our critical point. So here we need to find critical points, you know, because we are interested in sometimes in finding maximum, minimum, local maximum, local minimum, something like that. So let's find our critical points. So what are critical points? Critical points are where the first derivative equal to 0 or the first derivative does not exist, right? Does not exist. So using that you can find all critical points, and then once you have all critical points, you can find a local axioma, right? You make a chart for the first derivative. I write a chart for the first derivative. This chart should look like this. Here you have x, here you have y prime, here you have y, right? In the first row, you express the domain of the function and all critical points and all special points in here. For example, in negative infinity, positive infinity, and you have x1, x2 in here, right? Like at x1 and x2, suppose at x1, x2, the first derivative is equal to 0. So you have three intervals in here, and you need to find the sign of the first derivative in each interval. We need to find the sign of the first derivative because we want to see how the derivative change the sign, right? Go from positive to negative, go from negative to positive, or does not change the sign when x pass through, x1 or x2, because that is important. Thanks to that, we will know at which point the function attains local maximum or local minimum. For example, if the first derivative looks like this, plus, negative, minus, or plus and negative. So I know exactly the function in this interval is decreasing, and here the function is increasing, and then the function is decreasing, right? So if I ask you to find open intervals where the function is increasing or decreasing, you can make the chart like this, and then you do conclusion. The function is decreasing on negative infinity to x1, right? Union with x2 positive infinity. And the function is increasing on x1 and x2. That's it. At the same time, using this chart, you might see at this point the function attains local minimum, right? And at this point the function attains local maximum. So that is called the first derivative test, right? So I think that is all about the first derivative you need to know, and that's the application of the first derivative. Find critical points, extreme points, you see, and then we'll see where the function attains maximum minimum. And we still have another problem related to the first derivative, that is to find global axioma in some closed interval. So that problem is easier. So I will remind you about it once we consider concrete problems. Okay, and let's talk about second derivative. Second derivative helps us to understand the convexity concavity of the function. So again, you see, in here we need to find the first derivative helps us to understand where the function is increasing, decreasing, or where the function attains local maximum, local minimum. But the second derivative helps to understand convexity, concavity, convexity, concavity. And in order to do that, we need to find inflection point, right? Inflection point. Similarly to critical points, inflection points are points where the second derivative equal to 0 or the second derivative does not exist. So we need to consider two cases. Some students just forgot, Yeah, we put everything equal to 0, that's good. But sometimes we forgot about this case, right? Don't forget about that. And then you thanks to this, you make the chart for the second derivative. Again, you need to consider where the second derivative is negative, where second derivative is positive. So let's say if the second derivative greater than 0, the function is convex, right? Convex. So I used to write convex looks like this, and when the second derivative less than 0, the function is concave. Concave looks like this, right? And when the second derivative is equal to 0, so that is inflection point. Using these properties, we have the second derivative test. I write here because I don't want to erase what problem. So we have the second derivative test. How does it work? It says if you have suppose x, you have x0 as an extreme point, right? Critical point. You plug x0 into the second derivative to find second derivative, right? Just to find value second derivative x0. If the second derivative at x0 is greater than 0, so that is your local minimum because the graph looks like this. So that is the point, right? So that should be local minimum. If this value is less than 0, so this is your maximum. That is the second derivative test. Okay, so I think basically in this chapter we learned the first, second derivative, different differentiation rules, and we still have the Rome theorem and the mean value theorem. So now just go ahead to solve problems, right? And then in some cases I will remind you about theory. So the first problem, find the critical numbers of functions. Our function looks like g t equal to t 13 minus t for t less than 12. So again, for critical points, we need to find derivative of this function. So let's take derivative. Here we have product, right? Product of two functions. I use the product rule. Derivative of the first function is just 1, so I don't write 1, I write just 13 minus t, right? Plus t times the derivative of the second function. For the second function, I will rewrite in the following form: 13 minus t to 1/2, right? And when you take the derivative of this function, you use the chain rule. The chain rule says, okay, first I take the derivative of the outside function, which is 1/2, right? And I reduce the power by 1. So I have negative 1/2 in here. I copy all things in here and put in this place. And then I need to take the derivative of the one I just got, right? So that is negative 1. Don't forget about parentheses, otherwise you get wrong, you know. And here I just copy everything and put this into this place. I get 1/2, 13 minus t to negative 1/2, and times negative 1. All right, now what is the next? The next I will just simplify and put them together because I need to find critical points, right? And then I have 13 minus t plus. Okay, here we don't have plus, but we have negative, right? You have negative 1 and negative 1/2. So I have negative. Here is 2 times t on the top, right? T is still on the top, you see? This is still on the top. So what is negative? The power of negative 1/2. 13 minus t to negative 1/2 equal to 1/13 minus t to 1/2, right? And 1/2 is just, square root of 13 minus t. So I will just rewrite this in this form, 2 times of square root of 13 minus t. You see, and that is our derivative. And now we have to consider two cases. The first case, the derivative equal to 0, and the second case, the derivative does not exist. So probably the second case is obvious, right? Because you see the derivative, this function is okay, but this function is not defined at 12, at 13, right? Oh my goodness, I forgot. We consider t less than 12, so everything is okay with this function. So since t less than 12, this function is also well defined. We are good. We don't have the second case happen. Means the first derivative defines everywhere. Okay, so we have only one case to consider when the first derivative equal to 0. Let's say now I will set it equal to 0, right? You see, a minus b equal to 0 means a equal to b, right? So I have 13 minus t equal to t over 2 times 13 minus t. And now I use cross multiplication. I bring this to the left hand side. I have the following one. I have 2 times 13 minus t equal to t. You see why? Because here's square root of 13 minus t, right? Square root 13 minus t. So when we multiply them, we get just square of square root. That will be simplified. So I have this equal to t, and that means 36 minus 2t equal to t. And now I add 2t to both sides, right? So I have 36 equal to 3t. And t is equal to 26 over 3. And we need to check. Yeah, 26 over 3 is less than 12. Less than 12, so that's good. Our function has only one critical point. 26 over 3. Alright, second question. Find the absolute extrema of the function on the closed interval. So that's why I want to tell you, but let's do that right now, right? Gx equal to 3x squared over x minus 2 or negative 2 and 1. Find absolute extrema. Of course, we have two kinds of extrema, right? Local and absolute. In this case, we need to find absolute extrema of this function on this interval. Now let's check, right? What have is the function continuous? Here we have 2 minus x, right? So for any x in this interval, the function is well defined and continuous. We are good. And not only continuous, the function is differentiable. All right. And now let's see. Let's review the instruction how to solve such problem, right? First, I need to find all critical points, right? Critical points. Of course, critical points on this interval. And then I don't have to consider the sign of the first derivative, you see. We only need to find critical points, and then we compare function values at critical points and at two endpoints. We compare function values at critical point and endpoints. That's it. And when you compare those points, you can pick the maximum and the minimum. And those maximum minimum serve your like absolute maximum and absolute minimum. Okay? Okay, let's do this. So first I need to take derivative, right? Because I need to find critical points. So g derivative, in this case I have to use the quotient rule, right? The quotient rule says f over g derivative f derivative g minus f g derivative over g squared. That is quotient rule. So here's g x, right? So derivative of this guy is 6x, x minus 2 minus derivative of this guy, which is g prime, you see, is 1, right? So I have minus 3x squared over 1. X minus 2 squared Let's distribute and then simplify. I get 6x with x is 6x squared minus 3x squared is, okay, let's say 6x squared minus 12x minus 3x squared over x minus 2 squared, which is 3x squared minus 12x over x minus 2 squared. Now you see, okay, we have two cases, right? The first, the derivative equal to 0. So if I consider first case when the derivative equal to 0, that means I have to set g prime equal to 0. Of course, this is equivalent to that the top is equal to 0. So I have 3x squared minus 12x equal to 0. Here we have 3x squared, 12x, I can factor. This is nothing 3x, and inside I still have x minus here 3, here have 12, means here have 4, right? Equal to 0. And from here I would get x equal to 0 or x equal to 4, right? Because we said x minus 4 equal to 0, so x equal to 4. So for this case, we have two quick components, right? How about the second case? G prime does not exist. And 2. G prime does not exist at 2. But 2 is not in the domain. So we don't have to care about that. But 2 is not in the domain. You see, sometimes, yeah, you consider this case, and it turns out that that number is not in the domain, so we don't need to care. But sometimes that number is in the domain. We have to include that in the set, into the set of quick components. Overall, we have two quick components, 0 and 4, right? So let's move to the next step. Compare function values at quick components and endpoints. That means in this example, I need to compare f of 0 or g of 0, g of 4, what else? G of -2 and g of 1. And we have only 4 numbers. Let's plug 0, 4, -2, and 1 into the function. Let's find function values. Okay, g of 4, 0, 0, 0. This guy is 0. Right? This guy is 0. G of 4. I plug 4 into this, I get 316. 316 over 4 minus 2. Here I have 2, right? So I have 3 times 8, which is 24. This is 24. G of -2. Hard to find it. So I plug -2 into this, I get 3 times 4 over -2 minus 2. That is -3. So I have -3 in here, right? And then I plug 1 into this, 3 over -1 is 93. From here, you can pick the maximum, right? So the global maximum is 24. The function attains global maximum at 4. So that's your absolute maximum. And of course, this is absolute minimum. And the function attains absolute minimum at 2 points, 92 and 1. So that's how we solve this problem. Okay, next, determine whether Rolle's theorem can be applied to F. So we are talking about the Rolle theorem. What does the Rolle theorem say? The Rolle theorem says that if your function is good one, meaning differentiable, and at 2 endpoints, the function values are equal, means they are on the same level, right? Or when you connect this point, you get a horizontal line. And in this case, you have to find at least one point in between A and B. Let's say this is C, where the first derivative at C is horizontal. Because the first derivative is equal to is equal to 0 means the tangent line is horizontal. So you can see that again in the video on the Ron theorem. Now I just solved this problem, right? This problem asks to determine whether Ron's theorem can be applied to f on the interval. So our function is f of x equal to x minus 2, x minus 7, and x minus 9, and the interval is 2, 9. Of course, you see, the function is very good, right? Very well given, because you plug 2 into this, you get 0, f of 2, and you plug 9 into this, you get 0, again, equal to f of 9, and equal to 0. So basically, the function values at 2 and pos are equal, right? And of course, your function is polynomial. Your function should be differentiable, and differentiable everywhere. So the Ron's theorem can be applied to this function. So the answer is yes. From here, all right, and this is the first. The second, f is differentiable. From here, we can say we can apply the Ron theorem, right, for this function. Okay, next. So the Ron theorem says we have to find at least one c in between 2 and 9 such that by Ron's theorem there exists c in 2, 9 such that f derivative c equal to 0. And of course, we need to find c. So in order to find c, we differentiate that, right? Let's differentiate that function and then set it equal to 0 to find c. All right. So what is f prime? F prime. Here we have product of two functions. So I hope you still remember when I taught these topics, right? If we have a product of two functions, so you can write derivative of this equal to fg plus fg, right? And then you move this along f and g. So if you have three functions, you do the same thing, right? You write fgh, 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 right? And then you move first plus, second plus, third plus. So if we apply this, it would be easier, faster, I guess. Let's do that. What's the first derivative of x minus 2? It's just 1, right? So I have first term x minus 7 times x minus 9. You see, the first term. And derivative gh. Similarly, I have x plus 2, x minus 2, x minus 9 plus, the last one is x minus 2, x minus 7. And now we have to, distribute everything, right? So let me write that. First, x squared, so I have x squared in here. Here I have x with negative 9, I have negative 9, right? Negative 7, so I have negative 16x. In this case, 7 with 9 is 63. This is the first. The second one, I have x squared, okay, x squared, negative 2 with negative 9 is negative 11, and then 2 with 9 is 18, right? Plus x squared again, negative 2, negative 7 is negative 9x, and then plus 14. You see? Let's simplify everything, and we'll see what happened. Okay, I will keep this part. So you have x squared is 3x squared, negative 16, negative 11, and negative 9, 11 is 20, negative 16 is 36, right? 36x, and then 32 with this guy, so you have 81 plus 14 is 95, plus 95. That's okay. And we have quadratic formula, right? Equation. So in this case, we need to use quadratic formula, which is s12 equal to minus b plus minus square root of b squared minus 4ac over 2a, right? And you plug a, where a is 3, b is negative 36, and c is 95. Plug those, and then just find number. And that's it. And of course, once you got two values in here, you have to keep in mind that we are considering this function in 2, 9, right? So we just pick the point in between 2 and 9 only. All right. Next, find intervals where the function increasing, decreasing. Actually, we will do in this problem, we do the chart for the first derivative. We have function f of x equal to negative 5x cubed plus 15x plus 6, right? Find intervals of align short, increase, decrease, right? Align short. So, of course, we have to find our critical points. Our purpose is to make a chart for the first derivative. Don't forget about that. And in order to make a chart for the first derivative, we need all information, right, about the first derivative, critical points, and something else. So let's take the derivative of this function. I have negative 15x squared plus 15, right? Here is 0. So I have to set this equal to 0. The first derivative is polynomial, So we have only one case when x equals to 0. I factor that out from here. I get, just don't need to factor. Let's say 15x squared equal to 15x squared equal to 1, and x equal to plus minus 1. So the function has two critical points, right? Now let's make the chart for the first derivative. X negative infinity, negative 1, 1, infinity. 1 prime or f prime here is y. Okay, let's say at negative 1 and 1, the function is the derivative is 0 because they are critical points. So we have three intervals, right? We have to find the side of the first derivative in each interval. In between negative 1 and 1, I pick 0, and I plug 0 into the derivative. I get 15, means positive. In here, I can pick 2, right? And I plug into the derivative. I get negative. And here I pick negative 2. I plug into the derivative. I get negative. So negative means decreasing, increasing, and decreasing. And you can write, actually the function is increasing on where? On only negative 1 and 1, right? And decreasing on negative infinity, negative 1 union with 1 infinity. All right, and you still have another question. Apply the first derivative test to identify the relative extreme. So again, you need to use this chart, right? And you have to write directly in here. So actually, this part should be local maximum, and this part should be local minimum, right? And please plug negative 1 and 1 into the function, right? To find local maximum or local minimum. For example, you plug 1 into this, you get 95 plus 15 is 10, 10 plus 6 is 16, right? So 16 is your local maximum. Oh, sorry, here's local maximum. Here's local minimum. So negative 1 into this, you get 6. 6 plus 6 is 12. 12 minus 15 is negative 3. So negative 3 is your local minimum. Is it? All right. Next question, find all relative extrema of the function and then use the second derivative test if applicable. We have function f of x equal to x to 4 minus ax cubed plus 4 find relative extrema and then apply the second derivative test. Okay, so find all relative extremas. So we need to find all critical points, right? Take derivative. Equal to 4x cubed minus 24x squared. You set this equal to 0 and you factor 4x squared out, right? You get x minus 7 equal to 0. So from here you get x squared equal to 0 or x minus 7 equal to 0. Then x equal to 0 or x equal to 7. So you have only two critical points, okay? Two critical points. Now, if I want to use second derivative, I don't need to concede to make the chart for the first derivative, okay? So I have to find the second derivative, okay? X. Differentiate this one more time, I get 12x squared, and then here I have negative 48x. Okay, now we have second derivative. We have two critical points. I plug two critical points into the second derivative to see, right, the sign of it. And then based on that, we do conclusion. For example, we say x equal to 0, second derivative at 0 is 0. But you see, you plug 0 in here, you plug 0 in here, you get 0. So that is not extreme point, right? That is inflection point. And then at x equal to 7, you get f2 prime 7 equal to, you plug 7 into this. I just need to see the sign. So sometimes I don't need to find a concrete number, concrete answer of this. So I prefer to see the sign. Let me do the following way. I factor 12x out, I have x minus, so 12 I have 4 in here, right? So you can see, when I plug 7 into this, I get 7 in here, and then here is 3, which is positive. So in this case, f2 prime at 7 is positive. This is your minimum. That's it. All right. Next question. Find limits. Limit of square root of x squared minus 8 over 2x minus 4 when x goes to infinity. Let me remind you another one. X squared minus 8 over 2x minus 4, but when x goes to negative infinity. Okay, so why do I put limit in this chapter, right? Because we study limit to determine asymptotes. Limit at infinity, has to determine horizontal asymptote. Okay, so that means in this case we need to define horizontal asymptote of this function. So don't forget when we have square root of x squared, you see they are the same function, but limit at different right directions, right? Here we go, we approach the infinity to positive infinity, but here we approach negative infinity. Okay, let me remind you about similarity, right? Idea. So you have similarity at infinity. At infinity, you have polynomial in here, you have polynomial in here, right? Polynomial in here, polynomial in here. So at infinity, x squared minus 8 over 2x minus 4 is similar to. On the top, I only pick the term with the highest degree. So I have square root of x squared. And in here, I have just 2x. Okay, we just pick the terms with highest degree. But in this step, we have to be very careful because we have to remove square root of x squared. So that is absolute of x over 2x. right? If someone just write x, you are wrong. And now we see, right? For the first limit, when x goes to part infinity, x greater than 0, and then absolute of x is equal to x. Okay? Don't forget about this. So the function is equal to the limit when x goes to part infinity equal to x over 2x, which is 1 over 2. Okay? But when x goes to negative infinity, you see, x less than 0, right? Since x less than 0, absolute of x is equal to negative x. And then, in that case, the second limit is just equal to negative x over 2x, which is negative 1 over 2. You see, they are different in size, right? So basically, what's that? What does that mean? The limit of this function when x goes to part infinity is 1 over 2, and here is negative 1 over 2. That means y equal to 1 over 2 and negative 1 over 2 are horizontal asymptote for this function. Okay? So y equal to plus minus 1 over 2 are horizontal asymptote for the function square root of x squared minus 8 over 2x minus 4. All right, so the last question, analyze and sketch a graph of the function. Let me do that real quick, and then we finish this review. That's why I told you, right? The main purpose of this chapter is analyze and sketch graph. So let me analyze and sketch graph of y equal to 3x to 4 minus plus 4x cubed. So basically, now we have to compare everything. First derivative, second derivative, asymptotes, critical point, something, everything about functions. We compile everything and then use those information to sketch graph. Let me take the first derivative, and that is 12x cubed plus 12x squared. And using the first derivative, let's find critical points, right? We set this equal to 0. So you have 12x squared, x plus 1 equal to 0. From here you get x equal to 0. From here you get x equal to negative 1. Okay, so the function has two critical points. Once we're done with the first derivative, I recommend you to make the chart for the first derivative right away. So I write x, y prime and y, negative infinity, negative 1, 0, and positive infinity. And here the first derivative equal to 0. Now let's consider the sign, right, and see where the function is increasing, decreasing. So in here I can pick negative 0.5. I plug negative 0.5 into this, I get positive. And here I have square, so this is still positive. Okay. In here I can pick 1. I plug 1 into this, I get 1 square. 1 is positive. In here I can pick negative 2. I plug negative 2 in this, I get here square is always positive. But negative 2 plus 1 is negative 1. So I get negative in here. Overall, the function is decreasing from negative infinity to negative 1, right? But, it looks very strange, right? But increasing from here to here. The interesting thing is that 0 is critical point, but, the derivative does not change the sign when x passes through 0. So that's why the function keep increasing. Okay? So that is your local minimum. In order to find that, we plug negative 1 into the function. So when you plug negative 1 into the function, you get 3, and then minus 4 is negative 1. So negative 1 is local minimum. Okay? So we know when the function is increasing, decreasing, we know local minimum, right? So what is limit at negative infinity and in here? At negative infinity, the limit is equal to infinity. Is positive infinity. Is positive infinity. So basically, we know a little bit about function. Function looks like it, but we still need to analyze inflection points. And where function convex concave, right? So let's do the second derivative. Take derivative of this guy, we have 36x squared plus 24x. And we set this equal to 0, right? We get, in here I get maybe 12, just 12x now. Then I have 3x plus 2 equal to 0. So this is x equal to 0. Or from here I can guess x equal to negative 2 thirds. So negative 2 thirds. The function has two inflection points. It's very interesting. Now let's make chart for second derivative x. Y to prime y, negative infinity, negative 2 thirds, 0, infinity. We have 0 in here, we have 0 in here. In between them, for example, in here I can pick 1. Let's consider this first, right? 1 plug 1 into this, I get positive. In here I get probably negative. Yes, I get negative because this is positive, but this is negative, so I have negative in here. In here I pick negative 1, I plug negative 1 into this, I get positive. So the function here is convex, looks like this. Here is concave, look like this. Not exactly, but you know, here is convex again. Look like this. And now you say, where's that? One inflection point is 0. This is right here, right? This is inflection point where the function changes convexity concavity. Another point is interesting. Another point, where's that? Did I do something wrong? I'm curious. Let's say at negative 1 over 2. So you plug 2 into this, you have convex, you have concave, then you go back, you go up, you get convex again, right? Yes. 1, 2, 3, yes. Okay. Now let's sketch the graph. In order to sketch the graph, you see we have all numbers in here, right? Let me express that. So the first is 0, 0. You plug 0, you get 0 here. Function should pass through this one. The second, negative 1, negative 1. Negative 1 and negative 1. You see? Negative 1 and negative 1. Since this is local minimum, I write local minimum looks like this, right? Okay. And then if we want to find all x y, let's find all x-intercept, right? X-intercept. Let me erase now x-intercept. We set this equal to 0 to find all x-intercept, right? So another x-intercept is, if you factor this out, you get 3x plus 4 equal to 0. So you get negative 4 thirds. That is another x-intercept. Negative 4 thirds should be around here, right? So negative 4 thirds. What is the next? So you have one x-intercept in here, and you connect this guy with this guy, right? This really will. Oh my goodness, I'm wrong. I see something wrong here. Here should not be 2. Here should be 4. You see? No, it should be 2. Sorry. I'm good. So negative 2 thirds. Where's that? Where's negative 2 thirds? Negative 2 thirds is bigger than negative 1. So here's negative 2 thirds, right? Here's negative 2 thirds. At negative 2 thirds, the function changes convexity concavity, right? Go from convex to concave. So see, if you make this, you plug negative 2 thirds into the function. You plug negative 2 thirds into the function, you get what? Because we need to find that point, right? So actually, negative 2/3 times 3, and here take to 4, and then plus 4 times negative 2/3 cube, right? Well, basically, how to calculate this? Negative 2/3, I get negative 2/3 cube out, and then I get negative 3 times negative 2/3. That's negative 2 plus 4 is 2, and then have 2 in here. 2 times negative 8 times 2, and then here is 81, right? So negative 16 over 81. Negative 16 over 81 should be around here. So that is inflection point. That is negative 16, 81. All right. Just plug negative 2/3 into the function, right, to find that number. So basically, you have this function. You see, the function is convex, right? Convex from here, right? And then change to concave, right? Turn to concave to 0. See, change to this function from here change to 0. But after, when x pass through 0, the function becomes convex. So function should look like this. So that is the graph of our function. You see, yeah, sometimes we need more experience to make that faster. All right, so I hope that this review helps you a little bit to prepare to the quiz and to prepare to the test after the prep. Okay.